Hi everybody, today I'm going to be discussing the Great Oxidation Event. First, I just want to go over what I want to cover today. So the main questions I want to answer today for y'all is, what is the GOE? When did it occur? Why did it occur? How do we know? How did it change the environment and biological evolution? And were there multiple oxidation events in Earth's history? So I'm going to be answering all these questions for you today to at least the extent that I can fit in this video, and I hope you enjoy. First, let's just go ahead and answer all three of the first questions at once. So what is the GOE? Well, the GOE is the Great Oxidation Event, and it marks the first appearance of appreciable O2 in Earth's atmosphere. So that is free oxygen, like the oxygen we breathe, in Earth's atmosphere. Second, when did it occur? The GOE occurred kind of anywhere in between 2.4 to 2.2 or 2.1 billion years ago. I hear a lot of different ranges, but mainly around 2.3 to 2.2 billion years ago, I think is kind of the median. And that's just because we have a lot of different lines of evidence that point to around this time in Earth's history that oxygen was clearly doing something to mess a lot of systems up and change them radically. And so that's when we know it was accumulating. And so it wasn't like a, oh, boom, snap of a finger event. It was over a pretty long time, especially if we're thinking on human timescales. But on a geological timescale, it was a pretty sharp event, which is why we call it the Great Oxidation Event. 3, why did it occur? Cyanobacteria. Cyanobacteria were oxygenic photosynthesizing bacteria. However, there were cyanobacteria that did survive on other processes like anoxygenic photosynthesis. However, it was the oxygenic photosynthesis that began this oxygen revolution. And basically that just means photosynthesis that leads to oxygen production. And so these guys came along, they started producing oxygen, and they became ubiquitous in the environment, and oxygen just started accumulating like crazy in the atmosphere. And they formed these fossilized bacterial mats called stromatolites, like this wavy looking rock picture here. So now that we have the first 3 questions out of the way, that is, what is the GOE, when did it occur, and why did it occur? Now we're going to answer, how do we know? What's our evidence? Geologic evidence, biological evidence, what's our evidence that the GOE occurred, and what's our evidence that it occurred during this time interval that I just told you? Well, we have fossil evidence, continental oxidation evidence, BIF evidence, which means banded iron formation evidence, and carbon, sulfur, and molybdenum isotopic evidence. But we also have a lot of other elements that we have isotopic evidence for, but I'm not going to go into all the lines of evidence today, because if I did that, this would be like an hour long, and you don't want that. So let's just go over these main 4 lines of evidence, and let's get into fossil evidence first. In terms of fossil evidence for the GOE, we mainly have the stromatolites, like I was showing you, or the fossilized cyanobacterial mats. We have other fossilized evidence, but this is really what I'm going to be focusing on today. And so the fossilized stromatolites have actually been found to be up to 3.5 billion years old. And so this kind of raises the question, well, if stromatolites, or in this case, the things that formed the stromatolites, cyanobacteria, were around long before the interval that we defined the GOE to occur in, which is around 2.4 to 2.2 billion years ago, then why didn't the oxidation event occur way earlier? So there was a delay between cyanobacterial evolution and oxygen buildup in the atmosphere. And this has to do with geochemical sinks for oxygen mainly, and also the fact that these cyanobacteria had to become ubiquitous in the environment in order to produce enough oxygen to really build up in the atmosphere. But I'm really going to focus on the geochemical sinks for this delay reason. And the reason for that is because these really did a good job of gobbling up all the oxygen that these photosynthesizing bacteria produced, meaning that elements that react with oxygen or can become oxidized that weren't oxidized, because before these things came along, there wasn't oxygen in the atmosphere. They had to become oxidized in order for oxygen to finally then be able to accumulate in the atmosphere. And what I mean by this is reduced elements such as iron, sulfur, nitrogen, carbon, etc. I'm probably missing a lot, but basically these kind of elements were in the environment as reduced forms, meaning they had electrons to give away, and oxygen really wants those electrons. So it's going to react with all of those elements before it starts accumulating as free oxygen 2 in the atmosphere and Earth as a whole. And so it had to fill these geochemical sinks before it could accumulate. Now, in terms of continental oxidation evidence, this goes along similar lines as what I was just talking about, but basically we have evidence for both red beds after the GOE and detrital before the GOE. And so these are just 2 examples of continental oxidation evidence, but what this means basically is red beds, for example, are red colored sandstones or paleosols that are coated with iron oxides, which is why they're red colored. Iron oxide is rust. And this iron oxide coating indicates to us that oxygen was accumulated enough in the atmosphere to cause iron to oxidize. Another indication of continental oxidation evidence comes from kind of an opposite view, meaning can we see evidence for a reducing environment before the GOE? Well, yes, we can. So detrital pyrite is just reduced iron sulfide compounds, and these pyrite grains were found in rocks before the GOE occurred, meaning this reduced compound was ubiquitous before the GOE occurred because there wasn't enough oxygen in the atmosphere to oxidize that iron yet. And then once the GOE occurred, there was. So this is continental oxidation evidence. Moving on to BIF evidence, this is probably one of the most famous lines of evidence for the GOE is the banded iron formations. And banded iron formations, all they are alternating layers of oxidized iron with chert or silica-rich minerals. You can see this in the picture to the top left. The red layers are those rusty oxidized iron layers, and then all the other layers are chert. Now, how could these have formed, and why did they form in a very specific interval? Well, you can see their occurrence throughout geologic history down at the bottom right here. This is a graph of when they first started forming, then kind of their peak of formation, and then their demise, where they stopped forming throughout Earth's history. So the way that banded iron formations form is that oxygen builds up enough in the atmosphere to eventually oxidize enough of the iron in the ocean to cause banded iron formation deposition. Meaning iron that's all reduced is going to become easily oxidized when oxygen starts to build up in the ocean. And so therefore, once it becomes oxidized, it's deposited as this red band of oxidized iron. And when this deposition ends, that indicates to us this geochemical iron sink for oxygen has been filled up, meaning that all the reduced iron has been oxidized now. And so oxygen is available enough in the atmosphere that the formation of BIFs terminated. However, this was the initial way that people looked at the termination of BIF formation, meaning oxygen was abundant enough in the atmosphere and the ocean that it had now oxidized all the available reduced iron and BIFs stopped forming. However, that's really not exactly what happened because a lot of other more recent lines of evidence point to other processes occurring and point to the fact that the oxygenation of the ocean during the GOE wasn't as intense as we once thought it was. More evidence suggests that the deep ocean was not fully oxidized until much later after the GOE, almost 1.5 billion to 2 billion years later, and this suggests that something else had to stop the BIF formation. So around 1.85 billion years ago, what was it that stopped the BIF formation? Well, now we think that sulfide formation is to blame for the lack of oxidized iron deposition after the GOE. I'm going to talk about this more after a few more slides, so hang on to that thought. I know you're wondering how in the world does sulfide formation have anything to do with these banded iron formations? Well, I promise you I'll get back to that, so hold on to it. First, let's go over the carbon isotope evidence for the GOE. We have the Lamagundi excursion. I'm sorry if I'm butchering that name. I have only read about this. I haven't heard people actually say it out loud. But regardless, this excursion of isotopes, basically an excursion is just when isotopes behave oddly. This excursion of isotopes is marked by highly positive carbon isotope values in carbonates deposited around 2.2 to 2.06 billion years ago, as you can see down here to the right on this graph. And this was within the GOE near the end of it, if not after it, and so clearly has some association. And the thought process here is that the positive carbon isotope values reflect high organic carbon burial rates. But why were there high organic carbon burial rates? Well, the increase of oxidative weathering of continental sulfides, so oxygen in the atmosphere increased, and this oxygen in the atmosphere increased the rate of sulfide oxidation, meaning oxidative weathering of sulfides, turning them into, or oxidizing them into, sulfate, and then causing increased production of sulfuric acid, and that caused a subsequent increase in chemical weathering because sulfuric acid is acidic, obviously, and acids cause chemical weathering of sediment, and this can cause chemical weathering of phosphorus-rich sediment, which it did, and it led to an increased flux of phosphate to the oceans during this time. And then this phosphate, once having reached the oceans, increased rates of photosynthesis and carbon burial, causing positive carbon isotope ratios in inorganic carbon. And if you've seen my carbon isotope video, you know that positive carbon isotope ratios in inorganic carbon mean increased rates of photosynthesis, because organic carbon would have taken up all those really light carbon isotopes and stolen those negative values away from the inorganic carbon. And if you don't know what I'm talking about, go watch the carbon isotope video. But anyway, this is what the Lamagundi excursion is and how it also relates to the oxidation of Earth's atmosphere. We also have sulfur isotope evidence for the GOE. Now, the sulfur isotope evidence, as you can see, is just absolutely beautiful and is probably one of the most valuable pieces of evidence we have for the GOE, which is why it's so important. So when you're looking at this graph, you can see, if you have watched some of my isotope videos, that there's a triangle in front of that 33S on the y-axis rather than a normal delta symbol that we use for isotopes. So you might be wondering what that means. Well, this graph is showing MIF and MDF fractionation. And what these stand for is just mass-independent fractionation versus mass-dependent fractionation. So right away, we can see that mass-independent fractionation dominated on early Earth until the GOE, and then mass-dependent fractionation, which is typically how isotopes fractionate and how we understand them to fractionate in today's environment, was occurring throughout Earth's history since the GOE. So if we understand how these different types of fractionations work in sulfur isotopes, basically MIF is caused by dissociation of sulfur dioxide in the upper atmosphere by intense UV light. And this was occurring in the early atmosphere and today's atmosphere. But in the early atmosphere, these dissociated products remained isolated and therefore got preserved in sediment, and we can measure those fractionations and see that they were mass independently fractionated. However, in today's environment, those mass-independent fractionations of sulfur dioxide in the upper atmosphere are still occurring, but they don't get preserved in the sediment. And this is because once the atmosphere became oxygenated enough to oxidize any reduced sulfur compounds just hanging around, all those disassociated products from this MIF process would always just get reoxidized before being preserved on Earth's surface. And so the reoxidation of these compounds just caused refractionation and basically erased the MIF signals. And therefore, MDF was preserved from the GOE onward. Also, if you want to hear more about sulfur isotope fractionation and more on how this works, you can watch my sulfur isotope video. Our last isotopic piece of evidence we're going to look at is in molybdenum isotopes and molybdenum enrichments, because both molybdenum enrichments and isotopic ratios in ancient sediments can give us an idea of whether the conditions during that molybdenum deposition were oxidizing or reducing. And reducing is just not oxidizing. So here you can see that in this top right diagram, molybdenum remains dissolved when water is oxygenated, has free oxygen in it, and molybdenum gets incorporated into sediment, does not remain dissolved in the water column, when the water is euxinic. And euxinic, as we'll learn in a few slides, just means anoxic and sulfidic. So no oxygen and has a lot of sulfide in it. Remember when we were talking about BIFs and sulfide? Well, we're going to get back to why sulfide is so important in early Earth and why it has a relationship with depleted oxygen. So in terms of molybdenum evidence for the GOE, we do have molybdenum enrichment and isotopic evidence from sediment that supports the findings on the timing and intensity of the GOE based on other lines of evidence. However, I'm going to focus more on molybdenum signatures when we're discussing oceanic anoxic events and later oxidation events in Earth's history, and this is because molybdenum plays a bigger role in providing evidence for euxinic events. And so if you want to hear more about that, you can watch the video that I'm going to make on ocean anoxic events and late Proterozoic and Paleozoic oxidation events. So now that we've basically covered what the GOE is, when it occurred, why it happened, and how we know it happened, let's get on to how did it change the environment as well as biological evolution. Well, most people, when they think about when oxygen first arrived, they're probably going to think that animals that could breathe that oxygen also arrived in a similar time. However, the Cambrian explosion, which I indicated here on this timeline, marks the first appearance of large, complex animals that could breathe oxygen. However, as we see with the timeline, the Great Oxidation event happened almost 2 whole billion years before the evolution of this complex oxygen-breathing life. Why did it take so long for these animals to evolve? Shouldn't the GOE have triggered that evolution relatively soon after the event? This is going to come back to what I talked about when we talked about BIFs. I talked about how initially we did think that the Great Oxidation event was just a one-off, super oxidized Earth event that caused the oxygen in the atmosphere as well as Earth's ocean to increase to the point to where it was basically where it is today. However, more recently, it has been proposed by a wonderful scientist, Don Canfield, that the ocean remained euxinic, or anoxic and sulfitic, at least in its deeper parts, long after the GOE, not until the late Proterozoic, so before the Cambrian explosion. So this was an almost 1.5 to 2 billion year period where after the GOE, the deep ocean was still anoxic, and the surface ocean, as well as the atmosphere, weren't nearly as oxygenated as everyone had previously thought. It had only increased the oxygen content of the atmosphere to about 10% of the atmospheric oxygen on Earth today. With this information, we see that this Great Oxidation event was not nearly as powerful as we had once thought. It was a huge event and absolutely changed the face of Earth forever, but it wasn't a one-off, completely oxidized Earth event. The oxidation of Earth completely to the point that it is today was more stepwise. So going back to the BIFs, the banded iron formations, what the Canfield Ocean theory suggests is that the euxinic conditions of the deep ocean that ensued following the GOE ceased the deposition of BIFs in ocean sediments, because what happened was the increase in atmospheric oxygen caused an increase of continental weathering, like we talked about. We talked about oxidative weathering of continental sulfide minerals, and these continental sulfide minerals were oxidized to sulfate. Then sulfate was transported to the oceans, and this is where bacterial sulfate reduction took hold. Bacterial sulfate reduction is just a process in which bacteria can reduce sulfate to sulfide, and this is their metabolism. This is how they gain energy. So they were taking this sulfate that was coming in large amounts to the ocean from continental weathering and producing sulfide. And this production of sulfide was increased so much that it would have prevented further oxidation of iron after the BIF formations. And this would have instead promoted iron sulfide production, reduced iron sulfide minerals. And so we would not have gotten those BIF formation, those oxidized red layers of iron oxides. Instead, we would have seen more iron sulfide production and more evidence for black shales, which is a sediment caused by euxinic conditions. And so in short, the Canfield Ocean theory answers the question of why BIF formation terminated at around 1.85 billion years ago after the GOE. So now that we've gone through what the GOE is, when it occurred, why it occurred, how we know it occurred, and how it changed the environment and biological evolution, let's talk about whether there were multiple oxidation events in Earth's history. Well, I kind of already hit on this, but yes, of course there were. Based on what we just talked about, of course there had to be multiple oxidation events, because we just mentioned that the Great Oxidation event only oxidized Earth to about 10%, if that, of today's oxygen levels, meaning that there had to be more stepwise events. And the main one, besides the Great Oxidation event, occurred just before the Cambrian explosion, explaining why the Cambrian explosion was delayed. Those complex oxygen-breathing animals needed a bit more of an oxygen push before they could evolve, or at least that's what the evidence points to. And so you can see here this second stepwise oxidation event that occurred just before the Cambrian explosion in the late Proterozoic, or what we call the Neo-Proterozoic, caused oxygen to increase almost to its present day levels, leading to way more oxygen on Earth, not only in the atmosphere, but also in the oceans, which was really what boomed evolution, especially for large oxygen-breathing eukaryotes. So the last thing that I want to leave you guys with before I let you go is kind of a question for you to think about. Well, we just said that the Cambrian explosion marked the first appearance of large complex animals that could breathe oxygen. My question for you is, why did oxygen allow life to become more complex? Why couldn't it become complex before? And when I say complex, I just mean, more cells, more parts, different functions, more complexity of the cell. I mean, we had eukaryotes way before the Cambrian explosion, but up until the Cambrian explosion, prokaryotes were still kind of the kings of Earth. So why was life so simple before the 10% to 100% jump in oxygen? Well, I'll give you a hint. It has to do something with redox. I was going to leave you guys here, so you would have to go watch my redox video, but I'm going to give you a little more because I don't want to leave you hanging. So at least what I think is the reason based on my knowledge, this is kind of, I just added this in here because I think it's cool and I thought about it. So if I'm totally wrong, please point it out. But I think that the reason they couldn't become more complex until we had more oxygen is because oxygen respiration causes more energy production and therefore a greater potential for complexity. So when we're talking about metabolisms and energy production in different organisms, oxygen respiration is the best way to get the most energy production for what you're putting in. So the most net energy production from your metabolism. And we'll talk about that in more depth in a lot of the GeoBio videos as well as the redox video I mentioned here, but this is the basic concept. So with that, I hope this was helpful. I hope you enjoyed learning about the Great Oxidation Event and some of the lines of evidence we have to back it up. And I hope that you go out and do some more of your own reading because there's so much more on it that I couldn't even mention because of the time of this video, but it's really awesome. It's an amazing point in Earth's history, and it really just made our lives possible. So the next time you see some blue-green algae, wave hello and tell them thank you. And with that, I'm going to let y'all go. Thank you so much for watching, and I'll see you guys next time. Bye.